Good. So I'm Victor Gorbenko. I wrote down my email here just in case you have some questions, follow-ups for the lectures. You can also, if you Google this, you can find a website of my lab, see some things, description of some things I'm working on. So I'm here for this week. I gave one lecture yesterday that some of you were present. That was on a different topic. Was about confinement and a little bit of QCD strings. So this is another big aspect of fundamental physics that I'm working on, theoretical cosmology, and this lecture is called Quantum Field Theory in Cosmology, okay? QFT in Cosmology. It's going to be just 2 lectures. So as I gave this course, well, course with the same name, let's put it this way, about 2.5 years ago here. So it's also online. That one was more detailed, was like 4 lectures. So here it will be only 2 lectures. So I condensed it a little bit, but maybe I'll add some new stuff, especially some people took the course last time. So this is roughly the plan for the 2 lectures. 1 lecture today, 1 lecture on Friday. So we'll start with some review of evolution of the early universe, FRW space-time, and the Sиттера space-time. So we'll focus on it. Then we'll discuss cosmological horizon, causal structure of the Sиттера space-time, mostly, well, FRW and the Sиттера actually. Then we'll discuss the phase of observers and what are the symmetries of the space-times. And then, as I said, we'll start with some generic, for those, I'll explain what is a generic FRW space-time, but then we'll transition more to this particular case of the Sиттера space. And then, probably already in the next lecture, but maybe we'll start today, we'll start talking about free quantum fields, more or less. Okay, so quantum field theory in cosmology, maybe it's a little bit of an ambitious topic. So really we'll talk about free quantum field theory. And since most of you did not take QFT course, so probably it will already be something new. But then here we'll talk about free quantum fields in cosmological space, in particular in the Sиттера. And my hope is to demonstrate at least a little bit what is this theory of inflationary perturbations. And finally, I want to mention some things that I'm actually working on. A bunch of people are working on, including myself. Nowadays, we're trying to understand better, to develop connections between the Sиттера, okay, that we abbreviate as DS, anti-de Sиттера, and the sphere, okay? So we'll see how much time we have to discuss it. Maybe we'll discuss even a little bit the things like entropy of the Sиттера space, sort of some analogies to black hole spacetimes, but we'll see how it goes. Yeah, as I said, interrupt me many times. It's not very easy for me to normalize kind of the level. So if I'm saying something that does not make sense, if it's too complicated, then ask clarification questions. If what I'm saying sounds too easy, then feel free to ask some more in-depth questions. And okay, I'll try to then go a little bit in depth on these topics. Okay, good. So let's start with some introductions. So what is cosmology? Okay, so our universe, first, as far as we know, our universe has been expanding. And cosmology is basically the study of the evolution of this expanding universe. So we do not know if universe is finite or infinite, but roughly what we know, if there is some part of the universe that we can observe, and as I said, that it was expanding. Okay, so this is time goes upwards, and there's some cartoon for what the universe has been doing. So it's been expanding. Okay, and the size of this universe that we believe we have access to is something like 93 billion light years. Okay, and again, what we call the age of the universe, and really the age of the universe is the time for which we roughly think they understand how the universe was behaving. Okay, so again, the universe can be eternal in the past, but what we normally call the age of the universe is this length of the period that we're more or less confident about, up to some and this is 14 billion years, roughly speaking. Okay. So now what happened before that, we do not know, and kind of frankly speaking, what happens outside of this region in the spatial direction also, we do not know, but we can build some theories or have some conjectures, right? So just to give you, okay, it's not a very good comparison, but still, okay, how to imagine what is a light year, but okay, distance from sun to earth, right, it is something like 8 light minutes. So okay, universe is huge, and then okay, and it's also something like 150 million kilometers. Okay, so that gives us at least some comparison, some scale, which we can compare the size of the universe. Okay, so let me draw another diagram that I like to draw when I try to explain what cosmology is. So let's say this is time, and here let's put the object that we call a scale factor, a of t. So it's a little bit like a size of the universe, but really we don't want to call it size of the universe because it may well be infinite, right? But a of t is really the relative amount by which the universe has expanded, right? So then so it's basically here I'll draw this scale factor that explains this expansion, and it roughly behaves like this. Okay, let me say what this curve is. So now we're here at some time t naught, and the universe is expanding roughly close to exponentially with some parameter h naught t, which is called, well, in this case, Hubble constant or Hubble parameter. Now, before that, the universe was expanding at some sort of power law. Okay, this power law was changing a little bit, and okay, in detailed cosmology courses we discuss in details which power law it is. But for me, it's going to matter that it's some power law. Okay. And then, well, then I have here sort of I transition to dashed line, and so this is roughly t naught minus this 14 times 10 to the 9 years. Okay, this is what people usually refer to as a Big Bang. Okay. The plot is not to scale, of course, right? I mean, the universe expanded by some, many orders of magnitude since then, but still, that just to give you some intuition. So and then here there is a conjectured period. Well, I'd say that here there is some period that we keep really dashed, we do not know, but here there is a conjectured period where the universe again was expanding roughly exponentially, okay, but with some different Hubble parameter, and that was called inflation. As I said, this is still a conjecture, while this solid line is where we have, some really observation confirmations of what was going on. So now these both periods, current period of exponential cosmological expansion and this period of inflation, are closely related to the Sиттера spacetime that I will introduce. Okay, and that is a motivation, at least a practical motivation, to study it. Okay, so now let me say a few words about what is a quantum field theory. And again, I'll just start with some brief explanation. So, do people know what is a classical field theory? Okay, some examples of classical field theory we should all know, because at least we study electromagnetism, right? And electromagnetism, we talk about Lagrangian, of even yesterday we discussed, but so that's cool. Not yesterday, Lagrangian for electromagnetic field, and it is something like f mu nu, also equal to d mu a nu, d mu a nu minus d mu a nu d nu. Is it like this, right? D nu. No, it should be easier to write like this. D mu d nu a nu, right? No, not good. D mu a nu, d mu nu, and here we should have d mu a nu, d mu a nu, yeah, like this, right? No, I wrote the same thing, sorry. D nu a nu, right? Anyway, doesn't matter much. The point is that it is some quadratic Lagrangian of, and this field a nu, right? It depends. A nu is a electromagnetic potential, and this is, but from the point of view of like classical field theory or quantum field theory, we call it a field. Okay. Although electromagnetic fields, they're like E and B derivative of this A, but from the point of view of general field theories, it's we can still call A mu a field, and this guy depends on 4 space-time coordinates, right? So now the idea is that there are very general. This is a very general. So this is a classical field theory. So it's important that now everything, there can also be, for example, scalar field theories. Which is, roughly speaking, if we just take a scalar, call it the scalar potential, call it phi of x, let me call it like little phi of x mu. I can also write a Lagrangian that will describe a relativistic field theory. I just write d mu phi, d mu phi, right? And then, so this thing is Lorentz invariant if phi transforms as a scalar. Of course, this is just zeroth component of A does not transform as a scalar, but we can imagine a scalar function that, and then this object will be Lorentz invariant because all the indices are contracted, right? So this is a classical field theory. So now from this Lagrangian, we can also derive a Hamiltonian, right? Or Hamiltonian, well, Hamiltonian is an integral of Hamiltonian density, something like this, right? H of x mu d3 x, right? And then quantize this theory, okay? So now, once we have Hamiltonian, so now the complication is that there are infinitely many degrees of freedom. Any questions, by the way, about this picture I didn't pose? Is anything you want to? I mean, we'll discuss it in more details, but in case people want to clarify something, okay. So then we discuss what is quantum field theory. What is quantum field theory. It is basically a system. It's like a relativistic invariant, maybe right, Lorentz invariant. And first I start, indeed, I shouldn't contradict, in flat space, okay? Meaning in Minkowski, okay? Our topic eventually is quantum field theory in cosmology when we don't have Lorentz invariance, but for now let's sort of introduce what's the quantum field in flat space. So it's Lorentz invariant. Quantum sort of a tautology, quantum theory of infinitely many degrees of freedom, right? So this is sort of an important distinction from. It's really important that it's Lorentz invariant. So usual quantum mechanical system, usual apparatus of sort of standard Schrödinger equations. If one tries to merge it with Lorentz invariance, it first of all forces to introduce infinitely many degrees of freedom. It more or less forces them to be organized in terms of these fields. Okay. So this is, I mean, it is a big subject. I'm not going to explain why, but I'm just saying that so that this construction that we can say is motivated by electrodynamics, and okay, can be generalized to fields with different type of Lorentz indices, but it also more or less the most general way we know how to merge quantum mechanics and Lorentz invariance. Okay. So why is it infinitely many degrees of freedom, right? Because if we, for example, if we go to, if we transform phi of x t, we go to e to the I kx. Let's Fourier transform in space, for example. Okay, phi k. Of t, right? If we Fourier transform, then what happens if we introduce the Lagrangian, which is the integral dt d3x of our Lagrangian density, right? Then it will be roughly go into okay, maybe I. Okay, let me just talk about the Hamiltonian, right? Same thing for the Lagrange, but the Hamiltonian will become diagonal in momentum space. So it will be look like something like k squared fk f phi k, phi minus k, and then there will be something like pi k, pi minus k, where pi is the canonical momentum conjugate to phi, which is basically phi dot for free field. Okay, so now written in this way, written in this form, this is like an infinite sum, infinitely many harmonic oscillators. Okay, that's clear, right? Because we have a quadratic Hamiltonian, okay, and then they all just add up, right? I mean, if we replace integral with the sum for a second, then we just have infinitely many not talking to each other harmonic oscillators, right? And then, of course, we can add interaction, make it more complicated. So this is okay. This is in few words the formalism of quantum field theory. Okay, so I reviewed for you a little bit the homogeneous cosmology. Okay, just kind of how the universe is expanding as a whole, very briefly. Okay, I very briefly introduce to you what is quantum field theory. The important thing to remember is that it's like a relativistic version of quantum mechanics that kind of has infinitely many degrees of freedom. Well, I sort of get the assumption, okay, we wrote a Hamiltonian as a classical object, then we quantize by imposing, once we have harmonic oscillators, we know how to quantize them. Then we just impose canonical commutation relation for phi and pi, and then we go from there, right? So the idea, so the reason I introduced these two objects one after another is that because I want you to maybe to have a, okay, let me reintroduce my drawing. Okay, the reason I wanted to introduce this both object quantum field theory in cosmology is that so on top of this homogeneous evolution of the universe as a whole, of course we know that the universe is not completely homogeneous, that there are galaxies, galaxy clusters, planets, stars, all of this, right? So the idea that according to this, if this is correct, if this inflation thing is correct, then the prediction, whatever, prediction of inflation, and then if inflation exists, then this prediction also is true, is that all structure in the universe, okay, all structure in the universe, I mean all the fact that it's not completely homogeneous, that there are galaxies and there are like more galaxies in some places and fewer galaxies in other places. So all of these classical huge, black holes, whatever, in the middle of the galaxies. So all of this comes from, and I write it down because, okay, that's kind of the punchline. Let me clear more space. All structure in the universe originates from fluctuations, from basically how we call it, from ground state quantum fluctuations of fields during inflation. During fields, I'll write more in of fields in ds-like space-time during inflation. So this is I mean, I think it is a very one of the, again, it's still a conjecture. I mean, we have a bunch of, I mean, the theory is developed. There is some experimental, hints that that's correct. Some experimental confirmations. I probably, unless someone wants, I'm not really planning to talk about them in these lectures. But if true, it's, I think, one of the most beautiful predictions of modern theoretical and experimental physics of the last half a century or so. Since the theory was developed, that all that this huge classical objects, like the largest object we have in the universe, black holes, galaxies, and eventually, everything on the small scales, originally comes from tiny quantum mechanical fluctuations. I mean, quantum mechanical sort of has to be tiny by definition. Really, quantum fluctuations that then get enhanced and stretched by this expansion of the universe, and then they grow due to gravitational attraction. This small quantum fluctuation create gravitational wells for other fluctuations. They're going to fall into each other, grow, enhance, and produce all the huge classical objects we have in the universe. Okay, so that is really mesmerizing to me, and I hope in this couple lectures to give you, some flavor of how it happens and why we believe that that is true. Okay, let me pause. So there were way fewer questions the last time. Is it because I speak in English? If you want to ask a question, by the way, you can definitely ask a question in Russian. That will not be. I mean, I'll answer in some combination of.
What do you mean by the Sita line?
De Sitter like, because it's not exactly. Okay, I wrote that it's roughly okay. I did not even say what is De Sitter, so but basically, kind of going ahead of myself. De Sitter is when expansion is exactly exponential, okay, and with h being a constant. And here, during inflation, expansion is not exactly exponential, but it's sort of close to it. That's why I say De Sitter like. And yeah, let me say that the yes. So this. That should become more clear, yeah, okay, maybe it's a good question, but so far it's a little bit of a vague discussion, right? So I'm saying De Sitter like, yeah, basically because there are similar fluctuations in exact De Sitter spacetime. That's what we will actually going to discuss in the course, but then I'll mention there's some deviations from De Sitter space that do not change the picture too dramatically, okay, but.
It would be some perturbation around the ADS space.
About ADS.
Okay.
No, but you say, I didn't say ADS, I said De Sitter.
Yes,
DS space, yes, with some perturbation.
Space plus some perturbation.
Yes, that's at least the simplest inflationary models. I think at the level of, at the level of our course, we can think about inflation this way. There are more general inflationary models where somehow space-time is very different from De Sitter, but eventually the perturbations that are produced are similar. But okay, it's a little bit complicated to explain why. I think it's a sort of yeah, it's not such a big stretch to think that it's definition is some space and close to De Sitter. I think it's fine. Other questions? Okay, very good. Okay, then let me start going through these things in a few more details. So let's talk about one of these more topics that I mentioned, which is FRW state. So okay, so I formulated this sort of big claim, and now we sort of roll back and we start discussing the homogeneous evolution of the universe in somewhat more details, and then we'll discuss quantum field theory. Then we'll go according to my plan. We'll discuss the general structure of FRW and De Sitter spaces, and then introduce quantum fields in it. We'll see why there are some subtleties as compared to thinking about quantum fields in flat space, and then eventually hopefully we'll get to these fluctuations, okay, and then maybe it will become a little bit more clear why what this phrase means. Okay, so that's kind of the fall. Okay, let's talk about FRW spacetimes. So assumption. So what is FRW spacetime? It is homogeneous, isotropic, and homogeneous and isotropic. I don't know why I said the third spacetime. And by the way, I should say that so this way of things. So FRW stays for F stays for Fridman, Robertson, and Walker. But Fridman was really the first one to write down these solutions of Einstein equations that correspond to the spacetimes. And then as far as this picture that this is really applicable to the universe we live in, and this way of thinking that universe on large scales is homogeneous and isotropic, and then all the perturbations that we see, they average out on these large scales and sort of can be ignored. yeah, okay, well, that's what I said, that on large scales, large meaning, you know, still smaller than the total size of observable universe, okay, but large compared to scales of galaxy and galaxy clusters, universe is homogeneous and isotropic. And this way of thinking about it, I think really goes back to Zildovich, who really took it seriously, and was right. So now let's write down the Einstein equations for the metric that has this form. So we remind ourselves that Einstein equations, they have this form. Metric that satisfies these conditions of homogeneity and isotropy has to take this form, where Gij, let me write it like this. Let me say a squared of t Gij, okay, where Jij is one of three cases. It's either just flat three-dimensional metric that corresponds to curvature, spatial curvature, k is a spatial curvature equal to 0, or it's a metric of a sphere, let's call it S3, 3 sphere, that corresponds to positive spatial curvature, say equal to 1. Because I can normalize, I can always rescale my sphere by redefining the A multiplied by cos. So let's say unit radius, so unit curvature sphere, or three-dimensional. Yes, ds. I probably wanted to say ds squared, whatever. Ds squared of the indeed hyperbolic or Lobachevsky space, and that corresponds to k equal -1. And we can write down all these g's in a unifying form like this. Yeah. ds2 squares, where this is just a metric of a two-sphere. Okay, good. So now it's clear that if I say if I set k to 0, then this is just flat three-dimensional space-time in radial coordinates, right? It's a little bit less obvious that say for k equal +1, this corresponds to the metric of a sphere, and that's actually, I mean, I was advised to give you some exercises. So if you haven't done this exercise, so it's an exercise. Show k equal 1 is a sphere, okay, and actually it's some part of a sphere. Question also maybe which part sphere and which part. So I think it's a useful exercise, and the hint, at least the way I know how to do it, and it's a useful exercise on its own. I mean, even if you know other ways how to do it, I think it's good to do this way. Is consider embedding. Okay, embedding. What is an embedding? Embedding of sphere into four-dimensional Euclidean space, right? It's just an equation that tells us that we can have x1 squared plus x2 squared plus x3 squared plus x4 squared equal to, I guess, 1. in our case, maybe this one, I think it's 1, or maybe there's some, if I want to keep this k equal 1, maybe it's not 1, but I don't know, 2 or something like this. Okay, that's part of the exercise to figure out this constants. Good. Now, what is the Lobachevsky space? Okay, so some of you know, maybe all of you know, but let's still discuss it in terms of these embeddings. For Lobachevsky space, we can let's see, so that I don't mess the sign. So we embed this H3 into R1, 3, such a Lobachevsky space. We naturally embed in Minkowski space, and the equation will be something. I think it's this. If I don't mess it up, it's equal to minus 1. So let's see if I roughly got it right. So if we have our Minkowski space, so this is x4 and this is say x1. I mean, everything is clearly symmetric in x1, x2, x3, right? So that kind of corresponds to us having this sphere. This isometry is manifest, right? So let's draw the projection in x3 4 plane, so we can draw the light cone, right? And then what is it? So let's set this to this. So then that's where we get a hyperbola, right? We get a hyperbola that x1. Or what is it? It's easy to draw x4. X4 is a square root of 1 plus x1 squared, right? So it's something like this, right? Good. And then if we introduce 2 other coordinates, so I cannot draw, but then it gets rotated. It's kind of it's a dish like this. Okay? So the point of view, so this is what I call the Lobachevsky space or hyperbolic space. This is not any kind of special point. This spacetime is as symmetric as a sphere, right? So there is it's completely homogeneous. There are no preferred points on it, okay? So for cosmology, I mean, our universe can have this shape. Okay, so that's not excluded or not really. I mean, not okay. There are some theoretical bias, but it can be indeed of that space, and this is as good as far as symmetries are concerned as a sphere or as a flat plane. And the reason I want to bring it up is that later when we discuss de Sitter and de Sitter space, it will make this reappearance, this hyperboloids. Notice something curious, right? That it is, we start from a Minkowski space, but we get a Euclidean, it's a spatial, so this describes the spatial metric, right? So it is a fully Riemannian, not pseudo-Riemannian, Riemannian as opposed to pseudo-Riemannian, right? A fully Euclidean geometry that is embedded in Lorentzian space, okay? So there is nothing, the reason is that any vector we can get, any tangent vector on this hyperboloid is actually space-like, okay? So the metric on it is fully positive, definite. So as I said, this is exercise number 2. So this exercise 2 is show k equal to -1 is H3. Basically, one needs to find some parameterization of these 4 coordinates that solve this equation and compute the induced metric. You guys know what is induced metric from GR? Compute the induced metric and see that it indeed takes this form, both for a sphere and for hyperboloid. Okay, so flat metric in the embedding space induces the metric, if I start measuring distance over here, induces this metric. Very good. How long have I been talking? All right, 40 minutes. Any questions about this stuff? Good, 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 good. Then let me move on. Okay. So next step. So we have the to describe Einstein equations. We also need to know what is the energy momentum tensor. Let me actually erase this part because it was a little bit of a detour to remind you what is the hyperbolic space, what is a sphere. But I will keep the metric, and then we discuss the energy momentum tensor. And it has the form energy momentum tensor should have the form. Okay, good. So T mu nu, and we'll say that this is a perfect fluid. Perfect fluid, that is again, and that is an interesting also sort of observation. Maybe it's not obvious, but on large distances, say things like galaxies and stars and everything all together can be thought of as basically like a gas of particles, because on distance they're even bigger than the galaxy particles. So the whole matter in the universe can be thought of as like a gas of particles, and it's actually an ideal gas or whatever, which is an example of perfect fluid. Okay, so again, on this large distance is a good approximation. So if we have perfect fluid, it's characterized only by its velocity, u mu, only velocity, plus of course equation of state, to which we come back in a moment. But energy momentum, there is no other four vectors that can break that are consistent with the symmetries that we impose, homogeneity and anisotropy. But okay, fluid has some four vector, right? But there is no preferred three vector separately, right? Independently from the four components. So we can go. So then T mu nu has to be of the form. There are just two tensors we can build. There's some A, which is some function of time, times u mu nu plus some other B that is G mu nu. Okay, so there are only two tensors, two symmetric two tensors we can build, and that's explained in Landau Lifshitz, I think, whatever in the in many other sources, standard stuff. So now we can we can go to the rest frame of the fluid, and this is really the frame in which we have our FRW isometries respected. Okay, so that's how you should think about it. So we have some four-dimensional manifold. Okay, so let's say something like this, some four-dimensional manifold. And then you could ask, okay, in GR we don't, why am I writing this time here? What is this time? There is diffeomorphism invariance. How can I fix time? And the idea is that in cosmology, we have on top of metric, we have this space-time filling fluid. Okay, and this fluid, it has some rest frame. Okay, and then once we go to the rest frame of this fluid, which is also a frame where the density is fluid density is constant. This is where FRW isometries become manifest, okay, and that's what picks for us the preferred time coordinate. Okay, so this gives us, it's constant, gives foliation. What we call it foliation or slicing. In practice, what it means, it tells us that to each point we can sort of associate a three-dimensional manifold where the density of the fluid is the same, and so this three-dimensional manifold will be one of these three. Okay. So that's what's going on. So it's important to have this fluid. And then, of course, I can still do some time reparameterization, some time diffeomorphism t to f of t, right? So, but that I cannot, and that by this I can always achieve to have a -1 over here, right? So this is what defines FRW time. So don't, I mean, it's sort of a common question, you know, why I'm wearing GR, you know, why, how do I, like, what prefers this metric, why I'm not applying any diffeomorphisms to it, right? So nothing prefers this metric, it's just some parameterization of the sphere, whatever hyperboloid that I chose. We can do some diffeomorphism to the script, but really going into this, the reason we're justified to go in this form is because we have this fluid, right? So it's a physical, there's a physical system that partially fixes for us diffeomorphism invariance or whatever, or removes some of the diffeomorphism invariance here. Doesn't mean that the theory, of course, you know, is not diffeomorphism as a whole. Of course, it is, but there's a preferred gauge, if you like. Okay, preferred coordinate system, preferred family of coordinate systems, right, where at equal times the density of the fluid is the same. Good. So now, if we go to the rest frame and then also kind of approximate space-time with Minkowski, because that's enough, right? We just want to determine what are these constants A and B. If we go to rest frame, we go to Minkowski space-time, we fix A and B, and then okay, they're the same. Well, that's okay. I think we're sort of safe here. They're all closed, right? The windows. There's oh, okay, good. That's even safer. That's okay. I think it got maybe a little bit better. So then T mu nu becomes rho p p p. Okay, that is just the energy momentum tensor of ideal fluid from which we can determine A and B, right? So A minus B is simply rho, and B is P. So ideal fluid is characterized by density and pressure. Okay. By the way, who heard this stuff? Is that something new or? Okay, few of you. Okay, not everyone, but okay. So then, maybe if you hear it for the first time, then it's. But okay, I mean, I think it's. I think this stuff is sort of intuitive. I think it's intuitive. So then we have rho and p, and then we also need the equation of state. Equation of state for perfect fluid is p is a function of rho, right? So that what determines the equation of state. And in cosmology, it's common to pick a linear equation of state. So p is some omega rho. This omega is the thing that we fix, that we find for parameter that is well known. Okay, so we have p omega rho it's like just any equation of state you can linearize, right? That's basically the point, right? As always says physics. So that is, and omega is a constant. Good. So now that doesn't mean it means that there are some let me give you examples for radiation, electromagnetic radiation. Does anyone remember what is omega? No, 1/3 years. Because we want it to be traceless, the energy momentum tensor, right? Well, whatever. That's one way to remember it. And then for galaxies. Anyone has a guess what is omega for galaxies? 0. Okay, well, you guys took this course, so you know. But okay, but the idea is that you can, well, the point is that galaxies are so far away from each other that they basically don't, so there's no pressure. They don't interact. So you can compress them together. They don't, unless they start getting on top of each other, there is no interaction, right? And then also happens for dark matter, and then this is, we cannot get, but that's just from observation. For dark matter, also with whatever our measurements all suggest that omega equals 0. By the way, I should also tell you that from observations, k is consistent with 0. With observations. So we do not know if there is some curvature, some spatial curvature to the universe, but there are some bounds that I don't remember. For them, maybe I don't know. Okay, let me not quote the bound because it will take some time to introduce what it means. But curvature is sort of small. That's all we know. Could be positive or negative, but consistent also with being exactly 0. There's no reason to expect y will be exactly 0. And actually, it's some. Once we discuss maybe what is inflation, the idea that inflation also gives some justification for why curvature should be small. So it's the fact that curvature, we haven't observed curvature, it's one of these justifications, one of the reasons that support inflation. So I take this metric ansatz that I just erased, but you remember, right? And then I take this expression for the energy momentum tensor and plug it in the Einstein equations that I also erased, but okay, that's you remember. And then I get the following equations. Okay, let me be consistent with. Yes. Okay. Good. Let me not write this. So this is basically the 0,0 component of Einstein equations. This is the II component of Einstein equations. I mean, they're all the same by symmetries, and then no other non-trivial components, okay? And then we have also P equal omega rho. So we have two equations. Well, we have three equations, if you want, and three unknown functions, right? So we can solve them. So once we know the equation of state, we can find the solution. So now the idea that the solution, and again, I'll probably skip the derivation because it will be another exercise. That will be exercise 3. Is to show that the solution is A equal to A naught times some T times T, 3 times 1 plus omega. Okay? So this is why I brought up this the power law as a generic solution, right? Remember on my plot that for generic equation of states, so say there are different epochs in the evolution of the universe when radiation dominates, or say when dark matter dominates, and then there are different power laws, okay, that refer to this middle point of my plot. So now what happens? Where does exponential expansion come from? So you see that this formula becomes singular where omega is minus 1. Okay. Now omega minus 1, it is
Also this is in the case of k equal to 0, yes?
Sorry. You're right. Thanks. K equal to 0, yes. Thanks. I should have said. I wrote general equations, but this solutions is exactly. It's a bit more complicated to solve with non-zero k. But as I said, because experimentally relevant is set k equals 0, then that is fine. Good. Good. So what is omega equal minus 1 when this solution becomes similar? And that is clear, right? Because T mu nu becomes proportional to G mu nu. Okay. or well, T mu nu is proportional to, yes, to, in flat space, to eta mu nu, or basically, yeah, this term simply disappears, right? If P equal minus rho, then A equals 0, right? So this term is gone. And T mu nu is proportional to G mu nu. And that is this famous cosmological constant. So you remember, I first started writing it down separately in the equation because that's sort of historically how it happened. But really we can think, and especially in the context of inflation, that's very physically much more appropriate to simply think about cosmological constant as like a part of just a component of energy momentum tensor. If we have a component of energy momentum tensor that is proportional to G mu nu, or say it dominates our universe, then it corresponds to omega equal minus 1. So now let's say what is the solution. And then the solution, again, if we set k equal to 0, again, then the solution is A equal to E to the H T. Okay, where H is H you can see from here, right, that the also let's say from here eta squared or A squared, there's going to be H squared, right? If it's exponential, H squared is equal to lambda over m Planck squared. Okay, up to some, 3. That's G Newton. G Newton is 1 over m Planck squared, right? Up to some pi is blah 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 that I ignore. Any questions about it?
Where is rho here?
Rho, yeah. Rho, so rho is lambda, right? Because T mu nu is lambda G mu nu, right? We go here. This thing is 0 because rho is minus p, and then lambda, yeah, rho is lambda, and p is also lambda. Yeah, they have let's do dimensions. This rho is energy density, right? Should have dimension 4, and mass dimension 4, right? So lambda has mass dimension 4, then h has mass dimension 1, right? And that's consistent with the solution because time has dimension minus 1, so e to the ht, that's a dimensionless thing, right? So dimensions I got right, powers of like I got right, some order 1 coefficients, of course, don't keep track here. You can open any cosmology book or do it carefully yourself. Good. So now a curious observation. So now I told you that generic matter, it peaks for us some time foliation. But cosmological constant doesn't. So that is important because cosmological constant, it does not, because the energy momentum tensor, because there is no u mu component, right? So there is no 4 velocity. So nothing breaks, nothing fixes for us any preferred time direction, preferred time foliation. Okay? So to manifest itself, we can actually find a solution with, say, k equal 1, okay? And the solution is then A equal cosh ht. Again, let's for example solve this equation, right? To see that, well, again, let's solve this equation a bit simpler, right? We have sinh squared over cosh squared plus 1 over cosh squared. We have sinh squared when we bring each sinh squared plus cosh squared, which is sorry, what's going on? So we have sinh squared plus cosh squared.
We have parabolic sine squared plus 1 over cos squared, and that's 1.
Yes, yes. Okay, so this is why is that correct? Did I get the signs right? So we have Yes. Okay, good. Yes, we get 1. Sorry, yeah. You're right. 1 plus sinh squared is a cos. Yes, so we get cos squared over cos squared is 1, right? So, okay, good. Well, not 1. It's we get the power of h squared. So we should actually the solution. We need to be a bit more careful. Yeah, that's also we need to put here some power of h, right? Because we actually get in this case k equal h, right? In the way I wrote the equations, because when we have a dot squared, we get h squared times sinh squared, right? When we have plus h squared, and then we have h squared equal rho over m Planck squared, right? Okay, so then we can redefine okay, maybe if we want to have k equal 1, then I should write here 1 over h, right? Okay, good. Good. So now what happened? So we found a solution with the same matter content. We found a solution with k equals 0 and k equals 1. So you know the question: what does this FRW spacetime have? It has positive curvature or zero curvature, and the answer is that both. Okay. So let's discuss a little bit how it happens. So both of these correspond to the Sиттера spacetime. Okay. So this is sort of even a little bit easier to draw, right? So A is a cosh. So this is the Sиттера spacetime. It is some object like this, right? That first contracts, is infinitely large, contracts, and reaches some minimal size. And this, each slicing here is a 3-sphere. So that is my k equal 1 drawing. Good. So now you may say, okay, what is this? So that is clear, but how is it related to this k equals 0 drawings? Well, it turns out that this guy, and this guy is also a hyperboloid. This is actually also a hyperboloid. And I'll explain the embedding of it in more detail. But just for now, I want to tell you that this flat slicing, it's roughly a slicing like this. So these are constant t equal constant in k equals 0 slicing. Okay, and none of the two is preferred for the Sиттера space, okay, because there is basically no matter, because cosmological constant, it is sometimes, okay, we can, as I said, it's physically, you can think of it as matter, but originally people even thought it as just some term in the Einstein equations, right, because it doesn't, does not really behave like matter. No, this is not. We'll discuss in a second what is the static patch. It's not static, the metric, right? Because it's changing with time.
I mean this patch when we choose such slices of t constant, when we choose slices t constant not by circles, yes, by spheres, but like this.
No. This is what I want to say, that this is, again, my drawing is not perfect, but okay, we'll write down some equations, and maybe equations will be more clear than the pictures. This is really this, I claim, this corresponds to the flat slicing, to this slicing. So induced metric on this, each section, like I'm really slicing it with, yeah, like with planes, like this. And then each, here is dx, and then the way they are in this direction, so time goes kind of in this direction, and then they are expanding the slice. Okay, they go, I'm having half of my hyperboloid sliced with this. I'll draw a Penrose diagram, and then it will, and then we'll do and embeddings, and then we'll discuss what is a static patch. as well. Do people know what is a Penrose diagram? Who knows what is a Penrose diagram? Who doesn't know what is a Penrose diagram? Okay, a couple of people do not know. Good. So I'll review. What is a Penrose? So the point, the punchline is that drawing these pictures is a little bit confusing, because you see here, I mean, I make this claim, but then here, like this, it looks like this is shrinking the space-time, okay, according to global time. But then I'm saying that here it's already part of this expanding universe, because the exponent always grows. So it's not very clear what's going on here, and with help, drawing Penrose diagrams really helps. So let's have this little subtopic, Penrose diagrams. Good. So the idea is to map space-time into a compact manifold preserving trajectories of light. Of light, meaning preserving the light cone, okay? And preserving sort of trajectories of light. It's preserving the light cone. All right. So in particular, the metric, we can have the metric G is the same, G mu nu is the same as some omega, some function of x times G mu nu, right? Because the null matrix, that's what's called conformally equivalent, right? We multiply by a function, we do not change where the light cone is, right? So this is a manipulation where it's allowed. We're not going to change what I want to call Penrose diagram by multiplying our metric by omega, okay? Good. So let's do a little exercise for flat space. Flat space. So for flat space, we first go to radial coordinates, I guess. So we'll have some minus dt squared plus dr squared plus r squared ds2 ds s2. Right, I should write whatever metric of a two-sphere, right? The spherical coordinates of on a plane, and then we can introduce sort of light cone coordinates u, which is t plus r, and v, which is t minus r. Okay. So then this thing will look like something like du dv plus r squared of uv. By the way, this part basically more or less is ignored. It goes along for the ride in this Penrose diagram point. So we'll remember that each point is a sphere, okay, of some radius, but not very important. So let me stop writing it. So I get a du dv, and then so that's still not compact, right? But we can have instead. Let's see what's okay. We can have u. Yes, u is some tan alpha, and v as some tan times beta, right? And then, so this alpha and beta, they will change from, well, if these guys were going from minus infinity to infinity, alpha and beta would go from, say, minus pi over 2 to pi over 2. But because r is positive, there is some projection. So then, in this alpha beta coordinates, Minkowski space is basically the Penrose diagram of Minkowski space is this wedge. Okay, so this is r equals 0 line. Okay, and this is what's called null infinity. So you can see that light in Minkowski space, it goes on, on lines. As I said, the light still goes at 45 degrees. Okay, so that we go to this, and then our metric becomes, I should have written it, G becomes some omega times d alpha d beta, right? And then, from alpha beta, these are the null coordinates, right? And then I ignore this omega, I ignore the sphere, and that, the only thing that's important to remember is the sphere shrinks to 0 on this line, okay? So guys, for those who did not hear what Penrose diagrams are, does that make any sense? So I mapped Minkowski space into this wedge. And it now tells me, so this line is infinitely far away, that's infinity of Minkowski space, right? So, but that is okay, I can still see how light propagates, and in particular it's important that all points, so it's from this null infinity, each point of Minkowski space can be reached. And vice versa, if I take some source anywhere in Minkowski space, it always goes to this plus infinity, okay, never touches this, this is plus null infinity and this minus null infinity. Or past, future, this past.
Do we consider flat space-time?
That was example for flat space. I started with flat space, yeah.
But why every our point is S2 sphere instead of flat space-time?
Well, because I started with I started with writing the spherical coordinate for the special part.
Okay.
There is no answer why. It's just I knew that would allow me to succeed in mapping it into some compact picture. Okay, so other questions? Okay, good. So now we can do the same trick for the Sиттера space. Okay. What will be the difference, by the way, with the Sиттера space or with general FRW? What will be the difference with general, with general flat FRW? What would be the difference? Okay, let me erase this. I'll rewrite the metric of the Sиттера space later. So what would be the modification of this for FRW? For FRW, we have minus dt squared plus this a squared of t, and then the same thing, right? So now, to make it similar to this thing, I can go to conformal coordinates, right? I can introduce coordinates eta such that let me first divide by I first divide by a, and that's an allowed procedure because that's just some omega, right? So I can divide by a. Allowed manipulation, my goal to create a Penrose diagram. Now let me ignore the sphere again. And then now I introduce coordinate eta, conformal time. Such that dt over a is d eta, right? I can solve this differential equation. And that brings me basically back to the Minkowski problem. What is the difference? The difference is in which range eta, the only difference with Minkowski is range of eta. So range of eta depends on the fact whether the integral dt over a of t converges or diverges. Right, so in particular, if a equal 1, then integral dt converges at minus infinity and infinity, right? So that was just Minkowski, okay, sort of trivial. T is just equal to eta. But for example, if we have a as some power law, okay, say if a is a power law that is smaller than 1, which is say the case for like radiation or whatever. Then in the future this integral diverges. So future part of the so let me just write it. So if a of t, a is equal t to some alpha, and alpha is smaller than 1, then the diagram looks like this. There is future is the same, but then in the past there is some singularity. Right? Because we have singularity at t equals 0. Singularity at t equals 0, that corresponds to, some value of eta. Okay?
Sorry, how to choose initial conditions for this integral? Limits.
Well, it's kind of we start with the original, so if we have some FRW space-time, then say in this form, it starts from t equals 0 when we have singularity, and say it goes to t equal future infinity. So then we should integrate here from, so we say that t equals 0 is some eta, so we integrate from, for example, we can do. It's a bit of our choice because we can do some, we can redefine variable eta, right? But that's what, that's one thing that would work.
Okay, and for example, with cos h, if a is cos
Yeah, we're getting there. Yeah, we're getting there. So let's first do the exponent. Okay, if a is an exponent, then the integral is convergent at future infinity, right? Then t can go to minus infinity. I want to keep this picture. So we're getting here to the Ssitter, right? Which corresponds to the Ssitter, and I want to start with flat slicing. And then I have a equal e to the ht. T runs from minus infinity, to plus infinity, but eta then runs from minus infinity to 0, right? Because in the future, when t goes to plus infinity, that integral is divergent. And I can say that, to constant if you want, but I can always shift eta by a constant and call this constant 0. So then the Penrose diagram is like Minkowski, but it's only up to here, right? So it is this. Now, what is this line? So originally, generically for W, there would be some singularity at when t goes to minus infinity, a goes to 0. So we can imagine the metric is singular, but not for the Ssitter space, because something I forgot to tell you, but for the Ssitter space, I should have told you R is equal to constant, which is basically equal to h squared. up to some factor of 6, 5, whatever. Not 5, 6 or 3, I forgot. But there is no singularity, so t equal minus infinity is a coordinate singularity, but it's not a curvature singularity, okay, as you remember from Jar. Sort of like horizon in the Sиттера. This thing is indeed called Poincare horizon. I'll discuss horizon in more details later. So so this line is not so it's not a this is not the flat de Sitter, which is this wedge, is not geodesically complete. So how do we get the full geodesically complete Penrose diagram of the Sitter space? And that is indeed convenient to do in global coordinates. So
Could you repeat the reasons why it isn't geodesically complete?
well, because it's the usual situation when we have the coordinate singularity but not a curvature singularity, and then we can kind of have some, so we can send some geodesic that approaches this point, and we can actually calculate that it approaches it in some finite, proper time. And okay, because there's no curvature singularity, the question is, can we extend this space-time beyond that line?
Okay.
It's like for Schwarzschild. Are you familiar with Schwarzschild and horizon? Yes?
But it seems that there is a singularity in expansion universe.
Not for the Sitter, right? Because curvature does not blow up. So if we had some t to the alpha, then curvature is roughly like a double dot over a, and it's like 1 over t squared. So when t is equal to 0, curvature actually blows up in this case. But if we have a is e to the ht, a double dot over a is h squared.
Okay, see, but how to understand the fact that inflation has a singularity?
Well, we didn't get to inflation yet, so let's not run.
Different.
Let's not run. Well, that's related to the fact that inflation is not an exact de Sitter spacetime, if you like. Exact de Sitter spacetime is past eternal. I didn't explain it. I'm about to explain it, but yeah. So basically, if we look at the Sitter spacetime, I actually claim that this is not a singularity, and where I was going, I wanted to geodesically complete it. But you're asking a correct question. Why do I expect it to happen? And okay, did I answer it? That the curvature does not blow up here exactly for the Sitter. You see, if I had any deviation from the Sitter, then that wouldn't happen, and I would have some singularity. And more or less, that's when people say that inflation actually has some singularity in the past. More or less, that's what they imply. That it cannot be like an exact de Sitter.
Yes, thanks.
Other questions? Okay, so and I wanted already someone suggested that if we actually work with in global coordinates with a sphere slicing of the Sitter space, then a of t is a cosh, and the integral converges on both sides, right? So now so if we have a sphere, let me postulate the answer for you. It will take a little bit of time to derive, but if we work in, let me draw the answer for you. Let me draw the answer somewhere. Okay, I erase Penrose for Minkowski, okay? And I will occupy this space by drawing a larger Penrose diagram for global de Sitter. It's just a square. Okay, let me motivate for you. It's a square. So square, but this is not a boundary. This is the radius of S2. So this is global ds in sphere slicing. also known as global ds. So this is nothing but this, it's a map of this hyperboloid into this finite square. And you see, I mean, you shouldn't be surprised at this point that it has final extent in time in both directions, because this is basically eta. It's still the same formula, eta is integral dt over a, and then this integral from for the cosh, right? So the integral from minus infinity to infinity dt over cosh is finite, right? Now, the reason we don't have any boundary, spatial boundary, because unlike Minkowski space, the spatial geometry was already compact. So we didn't really need to do anything in the spatial direction. Okay, so I basically did it. I mean, let's rewrite the metric is, yeah, sorry, I'm overcomplicating things. The metric, or the interval, is minus dt squared plus a squared of t ds of s3 squared, right? And then I just go to minus dt of dt squared over a squared plus d squared s3 squared, and then I go to conformal time, right? So now this is the integral 1 over cosh squared. This integral is convergent, so I get just minus d eta squared, and this eta changes from like minus pi over 2 to pi over 2 or something like this, right? And then with the sphere, I really need to do nothing. Each slice here is an S3. This line is an S3, okay? So we can pick any parameterization of 3 with 1, it's compact anyway, right? And it's like of constant radius on this Penrose diagram because I factored out the scale factor when I went from this step to this step. So now the question is, so we're talking about the same space-time, okay? Same space-time. What is this guy? This guy is just this region. And the constant for W slices, they do something like this. So that's now I'm trying to clarify for you this picture. It's just, okay, one needs to, somehow I naturally selected, you see it's supposed to be the same thing. Just here I went with 45 degrees in this direction, and here, so this line is the same as this line. These blue lines are the same, okay? It just, I peaked, it doesn't matter, right? I mean, you can flip it like this and peak the other triangle, okay? So that's what I did on that picture. Somehow that naturally happened. Is that okay? I can redraw by reflecting it. Good. So now how do we convince ourselves? So I told you that this is like the same spacetimes. Of course, we can check all the metric invariants. We can think of this, and we can check that this metric, this cosh metric, and the metric with the exponent, they're the same. But the easiest way to do it is through embedding. So let me do the embedding, and then it will also help us to understand what is a static patch. So we try to develop some intuition about this de Sitter spacetime, right? That is a little bit, I mean, a little bit not even sort of simple questions are a little bit non-trivial, right? So embedding is given by something very similar to what we saw today for. So I embed de Sitter ds4 into 5-dimensional Minkowski space, okay? In the same way as we took 3-dimensional hyperboloid and sphere embedded as, say, 3-dimensional hyperboloid, we embedded in 4-dimensional Minkowski sphere space, 4-dimensional de Sitter space into 5-dimensional Minkowski space. Okay, generically it's not a 1, it's maybe I can do better. h2 minus 2, the radius of the zeta space, which is the inverse curvature. Good. So now let's draw the this 5-dimensional Minkowski space, okay? And remember, before we had a minus sign here, okay? So before we had so let's say this is x0 and this is, let's say, x1. So before we had x0 was square root of 1 plus x1 squared. So it was always positive. Now here we have we can say that x0 squared is x1 squared minus h squared, right? So x0 can actually reach 0, and then we have two branches of the solution. So this is the solution, and this is the solution, and they're actually connected because, okay, we can rotate in the transverse space. So before we had our hyperboloid here, space-like hyperboloid. Now we have a time-like hyperboloid, and this is just this drawing, okay? So now let's see, how do we convince ourselves that this is drawing? Well, let me actually find the embedding for you that gives the global coordinates. Okay, I can write it down explicitly. Maybe I do it for once. I set h to 1, okay. Good. So now, well, let me do indeed the exercise once for you, so that you don't get so surprised. So then we can compute what is ds squared, right? It's just induced metric. It's minus dx naught squared plus dxi squared plus dxd squared. Okay. And sorry, and I didn't write what is xd, but xd we just find from no, I includes d. Okay, I is 1 to d. Yeah, so this formula applies here because I have a constraint here. Okay, good. So we plug it in, and then what we get, okay, let me move. I just plug in this into this, right? So first, what is this? No, it's cos squared dt squared, right? Plus we get sinh squared t di squared dt squared plus d di squared, which is the metric on this sphere, well, on the three sphere, plus, okay, then there is a piece which is dt dzi zi, right? The mixed the mixed piece, but the mixed piece disappears. Okay, so what do I do next? So these guys just combine. So we have minus cos, so zi squared is 1. So this gives to us dt squared, sorry, dzi squared, sorry, I miss cos t, of course. Sorry. Well. right? I mean, it's just from this parameterization. Cos squared t, and okay, there is this here I missed cos times sinh, but it doesn't matter because this thing is 0 anyway. Okay, so good. So we okay, you see, right? So that thing is equal to minus dt squared plus cos squared t d squared on the S3, right? Which is just a metric on this 3-sphere. Okay? Good. So now, basically, the way to proceed is that we can find, so we have, we can also write down embeddings for Poincaré, for example, for Poincaré coordinates. Let me write down for you the embedding. Good. So for Poincaré, Poincaré, it means k equals 0 slicing. It's also called Poincaré slicing. That's just terminology, okay? That's when the metric is with A, it's this one, okay? It's the same, that's why I'm writing it here. When A is equal to ht, well, you write the following. x0 equal to sinh t plus r squared over 2 e to the t. x1 is equal to cos t minus r squared over 2 e to the t, and then xi is equal to e to the t yi, where where yi is just flat coordinates. Well, maybe I just write like this. Capital Xi is just little xi. Okay, good. So that is again a homework exercise, that this embedding, it actually parameterizes this part of hyperboloid, okay, and then the metric is this metric, okay. So that is, again, I don't have time to do it. It's a little bit more complicated what you'd hear, but again, you just take this stuff and plug in here. Okay, and see what metric you get, and what part, what is the range in which, when we change tr and this x, little xi, which part of the hyperboloid we span, okay? And the claim is that it will be, you will get this picture and this picture. So now, okay, the next thing that I have here, and should have indeed probably 5 minutes should be enough to discuss it. Okay, unfortunately we don't have the. Okay, maybe I erase this part. I erase this part because I want to keep Penrose diagrams. They're more intuitive, and I mean I have the hyperboloid kind of here. So I want to talk about the static patch. So static patch is embedding that looks like this. And then the metric of the static patch xi is r zi, and zi squared is equal to 1. And here I goes from 2 to d, okay, because x1 and x0. Good. So I want to get here and write to you the metric of the static patch, because that will be maybe something you will recognize. ds s2 squared. Okay, so the claim is that this space-time, it's part of the Sиттера space. It has constant curvature and everything, and it is static, and it looks actually very similar to Schwarzschild space-time. If you want, I can write for you the Schwarzschild space-time here. So Schwarzschild, I write it in different color. Well, green is invisible probably. Okay, I write in red the Schwarzschild. Okay, good. So you see, and then plus, of course, the same, plus the spherical part. But the idea is that there is this harmonic factor. So here we have 1 minus r squared, here we have 1 minus 1 over r, okay? But they look kind of similar. So we'll discuss it in more details in the next lecture, but first I want to draw the static patch on this diagram. And again, if you see this coordinate, you see which part of, because you see this, we have embedding, so we can go between all the coordinate systems, right? And see and this way we can see which, but the map is not so simple. If I actually try to invert and write, static patch coordinates, in terms of, say, this Poincare coordinates, it's going to be a messy formula again. It's fun to play with it, but I'm kind of telling you what the outcome is. But I showed you that we have global here, we have static patch, and we have Poincare. You see, they all, these capital X's, they're all the same, right? So I can now relate all of these coordinate systems. Okay, and the idea of the static patch, it is this region. Okay. The reason it's called static is, of course, now time translation is an isometry. I hope it's not confusing. This time has nothing to do with this time and with this time, right? Sorry, I should be calling it different letters, but okay, I forgot to do it, right? So the time, you can see from this picture. So say constant time in constant. So let's say the static patch. It will be this time was in red, and then in Poincare it is the blue time, right? So Poincare is blue lines. Global just these horizontal lines. Let me not draw them. Now static patch, it is something like this. So this is clearly constant time. Yes, it's something like this. You see, so what is a constant time and a static patch coordinate? It's not the same that is in global coordinates and not the same that is in Poincare coordinates. Okay? Good.
Are they just different parameterizations
of the same manifold? Yeah. But they have kind of different physical meaning. So once let me just advertise what I want to do in the beginning of next lecture. In the beginning of next lecture, I want to discuss in more details. So, for example, let's just say, we can have an analogy with Schwarzschild spacetime, but even here on the Penrose diagram, you see for static patch, this line is a horizon in the following sense. Imagine we have an observer that lives in the static patch, say along this line. So that's some observer. It's a time like geodesic along which an observer can live. Okay. Now this line is a horizon. What does it mean to have a horizon? Horizon means that this point, for all the points that are on this side of this horizon, they are causally disconnected from it. Signal from here can never reach this observer. Right? And the same is true so this is like a past horizon. So for this guy, this thing is like in the black hole interior. But let me draw for you the Penrose diagram for Schwarzschild. So the metric is the same. Similar. Sorry. So Schwarzschild Penrose diagram looks roughly like this. And then this line is a horizon. Okay, so this is singularity. This is like asymptotic Minkowski space. Now, what does it mean to have a horizon? Light from here, that's why Penrose diagrams are very useful. You can see that light from here cannot go outside, right? So it can only fall in the singularity. Something very similar happens here in the Sиттера space, okay, as far as this observer is concerned, because light from here, it reaches future infinity, but it can never reach this observer. And that's actually true. There are some, stars or galaxies which we observed because when they emitted some light in the past, so we measured them, and then they basically moved behind the this cosmological horizon. They fell behind this cosmological horizon away from us. And we will never be able to measure any, unless if the space-time, remains expanding like it does now with acceleration, being like the Sиттера space, we will never see them any signal coming from them again. Okay, but the difference between the Schwarzschild horizon is something absolute. Okay, while the Sиттера horizon is observer-dependent. Let me draw a new picture because this picture became a bit too messy. So you see, if I have another observer that say lives over here, then for them the static patch will be something like this. Okay. So now and then the original static, and then for this guy static patch is something like this. The reason this guy is a sort of, I don't know how we call it, like this and this is a triangle, it's every point here is a sphere, right? So these are the same manifolds, just this Penrose mapping makes them different. So you see at some point these guys were able to communicate with each other, okay? And then what happened, they ended up being behind each other's horizons. So in the Sиттера space, it's unclear, who. I mean, it's not that there is like some region that is interior and some region that is exterior, and that someone falls behind the horizon and the other guy doesn't. It's observer dependent. Okay. If I pick an observer, then there is immediately a horizon related to that observer in the Sиттера space, and then other stuff falls behind the horizon. But if I take a different observer, say some guys that live in this faraway galaxy that fell for us behind the horizon. For them, we fell behind the horizon. Okay? So that is the funny part about the Sиттера space, and that's what makes interpretation of physics, of some fundamental physics of observables, and what is measurable, what is not measurable, what should make physical sense, or what shouldn't make physical sense, very complicated in the Sиттера space. So inflation, which is a quasi-de Sиттера space, it fixes the situation in some way that we will discuss, I think, next lecture. Okay, so that's why this primordial fluctuations, this quantum mechanical fluctuation of quantum fields created in this original quasi-de Sиттера space that corresponds to inflation, are actually can be observed by us by a single observer. Okay, that's because. Well, I do not know. I think I'll explain this next time, because now it's that for now is getting a bit too late. So let me stop here for questions. Yeah. So as I said, next time we will consider on Friday discussing the causal structure of the Sиттера space. We'll basically start from these diagrams, and then we will talk. I'll talk about possible observables, and then we'll discuss these quantum fields that live in the Sиттера spacetimes, and I try to explain what are the cosmological fluctuations, and then we'll talk, if we have time, some connections to ADS and the sphere spacetimes. But okay, but for now, let me pause here and see the questions.
Как понимать, что у нас разная параметризация, разные части диаграммы Пенроуза написаны. То есть одна параметризация половину, другая четверть. Это кажется странно, что у нас не все пространство описывается разной параметризацией.
Yeah, well, that's what, okay, they're asking, is it strange that there are pieces that different parameterization cover different pieces? And I'm saying it's not, well, I won't say it's strange, it's a generic feature of, you know, some space-time that different coordinate systems only cover patches. The point is that in the Sиттера there are these, there are other coordinate systems that have interesting physical interpretation. But there are these three coordinate systems that have interesting physical interpretation. For example, the Sиттера space on its own is not static. There is no global time-like killing vector. There is no time isometer you can describe globally in the entire de Sitter space. That's why, but then static patch is a maximal submanifold of the Sitter spacetime that has time-like killing vector. Okay, so in this sense, if I wanted to find a metric, there is a metric of the Sitter space, okay, that corresponds to a solution of Einstein equation with positive cosmological constant, for example, that is static, that has time-like killing vector. You see, the metric does not depend on time. It could not be the entire de Sitter space, but it had to be some region of it. And okay, that's the region that we call static patch. Okay, it's kind of not a coincidence that this region is shielded by the horizons, although I don't think it's immediately obvious why that should be the case, but that's kind of the analogy with Schwarzschild, right? Also for Schwarzschild, there is the time-like killing vector exists, exists only outside of the horizon, right? And when we go to the horizon, the time-like killing vector switches to space-like killing vector. Of course, number of isometers is the same everywhere in the Sitter space. Okay, maybe I'll talk about isometers a bit more at time, but the killing vector that's here is just time translations. Here it becomes space-like. Okay, so and there is a different isometry that's locally here, looks like a time isometry, which is basically this guy's static patch time translation. But there is no global time isometry in the Sitter space. So there are physical reasons for why some of this parameterization shouldn't have worked for the entire space-time.
Yeah, I see, but it looks strange for me that sum of parameterization is literally bigger than other. It can mean that in some parameterization universe is also, it seems like, bigger than...
No, it's the same universe. It's again, we should just get used to the fact in GR that again, same for Schwarzschild, there's a Kruskal coordinates that work equally well, you know, inside and outside, right? And so that is again quite generic in GR. There is nothing, and I mean, from just geometrically, even if we don't talk about GR, we can talk about just some Riemannian geometry. I mean, it's still generic that there are some, also for the sphere. Say, think this coordinate that I wrote down, if I remember correctly, it only covers like half of the sphere. And then there are other coordinates that cover the entire sphere that are only singular at a pole, right? But you cannot have, for example, coordinates that are non-singular everywhere on the sphere, right? Because, okay, that's not a sort of trivial manifold, right? So this, I think that these things are quite generic. So there is no sort of mathematical surprise. What is, again, here, what makes it interesting is that there's different coordinate systems. Like, I mean, global is nice because it covers globally the entire space-time. The static patch is like this Poincaré one is nice for some other reasons that, again, I'll partially explain next time. But in particular, that it's the one that we actually use the most when we talk about inflation, whatever. It's the one that looks most similar to our universe, it's most natural from the point of view of describing our current universe because we seem to be having some preferred, we still not exactly in the city, we have a little bit of matter still, roughly 25% or something like this, that fixes for us coordinate system, okay, and it's closest to this blue flat slicing, right, because we observe the curvature is small. Okay, so when you have some small deformations of the Sitter space, like we do in real world, they sometimes kind of project us or tell us to use one of the coordinate systems because we're no longer dealing with exact de Sitter. So once you deform away from the de Sitter space, all of them become different, right? Because then you actually can have some preferred foliation depending on whether, you know, some of your matter fields take constant values on slices that are closer to the, say, to some of those. But whether that is kind of, okay, that's what maybe I'll talk about. But the philosophical question here is whether, say, the pure de Sitter case, where the entire de Sitter space should make sense, or if it's only the static patch that should make sense. Because you can be sort of like a radical, you know, like in, you can say that the only thing that makes sense is that, at least in principle, can be measured by, you know, some experiment. And by a single observer, okay? And here, everything is behind the horizon cannot be measured. So it's kind of a debate if it's some deep fundamental level, that part of space-time actually is real, or it's some sort of approximation or sort of illusion. But okay, but that goes beyond what we can discuss in this course. Okay, guys, I think that's it for today.